And now let us welcome our next speaker, Professor Shanti Bhattacharya. She will present on manipulating light with the micro and nano optics and holographic techniques. And she's also my doctoral thesis advisor. So let us welcome Professor Shanti Bhattacharya and let us know more about her from Daniel.
Absolutely. So, Professor Shanti Bhattacharya obtained her Ph.D. in physics from the Indian Institute of Technology, Madras, in 1997. She was awarded the Alexander von Humboldt Award in 1998 and worked in the Technical University of Darmstadt, Germany, for several years. She subsequently joined Analog Devices, Cambridge, USA, where she worked as a design engineer. She is currently a professor at the Department of Electrical Engineering, IIT Madras. She has served on the board of OSA, now called Optica, and is currently an associate editor of Optical Engineering and Journal of Optical Microsystems. Her current research interests are meta and diffractive optics, optical MEMS, and studies relating to imaging techniques. While she loves her work with light, she also loves her breaks, which, more often than not, involves escaping to the Himalayas for a while. She is an enthusiastic hiker and enjoys several outdoor activities.
Okay, so first of all, let me thank Vijay. It's always a pleasure, I think, to see one's students doing so well. And it's really an honor to be giving a talk here. So I'm going to be talking about manipulating light with micro and nano optics, and in keeping with the theme of the conference, we'll talk about some holographic relating to using holography. So there's a big need for beam shaping for many applications. And we all know that the common output of a laser has a Gaussian intensity distribution. But for various applications, you might need a flat top or a ring-shaped or a donut-shaped beam. And what I'm showing here, of course, is just the intensity variation of the beam. But there could be specific phase variation, which in turn represents a certain behavior. So, for example, the donut-shaped beam may have orbital angular momentum. So the research question that we are really asking is, how do we transform this typical output of a laser into any of these kinds of beams? And we need to arrive at the element that will do this transformation for us and get us to the desired output beam. So let me take an example of the Bessel beam. Maybe you want to convert your Gaussian beam to a Bessel beam. A Bessel beam has very interesting and useful properties. It's known to be propagation invariant over a distance, and it has a self-healing property. And you can see this comparison here between a Gaussian beam and a Bessel beam. If you start off with both beams of same core width, the Gaussian beam will start diverging fairly quickly, but the Bessel beam maintains that width over a much larger distance. Now, the problem, however, with the Bessel beam is that if you take a cross-section of the beam, may not be so obvious in this image here, but in this, the side lobes of the Bessel beam are much clearer, and those side lobes themselves pose a problem. You're using the central core for your imaging application or for whatever application, but you do have these side lobes, although of lower intensity, lower peak intensity, but they still do exist. So our requirement, and especially for applications like light sheet microscopy or OCT, is that could we get a Bessel-like beam which had the properties of propagation invariance and self-healing with the reduced side lobes? So there has been some work done on this earlier. Morey's group in 2015 had proposed using two slightly different Bessel beams and superposing them and actually creating a destruction of the side lobes, so that you could get a Bessel beam with much lower side lobe. So in a regular Bessel beam, the first side lobe has a peak intensity of 16% of the main, but you can see in the superposed one that the peak intensity has dropped quite considerably. So this technique involves taking two Bessel beams, and you're looking at the plane where these phase terms are equivalent. So you can just work with this intensity equation and minimize this over a certain distance, and this is the distance over which you are going to reduce the side lobes. Obviously, the energy has to go somewhere. So if you're reducing the side lobes here, it means that there'll be an increase in this region, but that doesn't matter because you're just trying to reduce the side lobes in a region close to the center. So you can use this equation and minimize it, and thereby optimize what should be the amplitudes of the individual beams as well as their KR vectors. Now, the problem with the earlier work, it worked and they were able to generate, but they generated their Bessel beams using annular rings. And so this is a very lossy proposition. A very small percentage of the light is actually coming through. And our work is to use a phase hologram to create the combined Bessel beams. So we basically add a tilted plane wave to this once the optimization is done, and then create a hologram. And then we can arrive at this side lobe suppressed Bessel-like beam. So this hologram pattern, in fact, we've done the optimization and arrived at the hologram. And this is the schematic of the hologram pattern with the phase varying as shown over here. And you can now put this graphic phase onto an SLM and illuminate. This particular experiment was done at the wavelength of 632.8 nanometers, and the side lobe suppressed SSB, which is in the desired order, can be captured through this from the reflected light through this iris. So these are the experimental results. So you can see that if you look at the central core, I'm not sure if it's clear, there are side lobes visible here, but they are of very lower intensity. And if you take a cross section, you can see that it's very reduced. So the optimization was actually done such that the design value of the Bessel beam was to have a core radius of 44 microns. And we were looking for a suppression of at least 40%, up to 40% of the side lobes. And in this experiment, we can see that we could get a propagation invariance distance of about 24 millimeters with at least 40% side lobe suppression. And if you look at the beam as it propagates, because of course you don't want the suppression to happen only at one plane, you want it to happen as the beam propagates. That is the Bessel-like behavior. And you can see that as it propagates over this distance, at this point, the side lobe is fairly high, but over quite a long distance, you can see that the side lobes have been suppressed successfully. So the technique works very well. But of course, we don't want to always use an SLM, and especially if you're thinking of an already complex system like light sheet microscopy, or you want to make a compact system like an OCT system, then you don't even need the tunability that an SLM offers. So it's enough to put this onto a compact element. And so we want to replace the SLM. Now, we can create our elements, of course, using refractive, diffractive, or meta-optics. But in this case, there's no refractive version that would work. You could take that phase and create a diffractive optical element. But the easiest diffractive optical element, of course, would be a binary one. And again, we are moving from the amplitude version to a phase version to increase efficiency. And you wouldn't get much of an increase in efficiency over here. So we are looking at using meta-optics, where by changing lateral dimensions, you can get different phase steps. And so in a single fabrication step, you can achieve a very high efficiency. We already have the phase we want. That was what was being put on the SLM. So that phase can now be uploaded into this tool. This is a software tool designed in my lab by a former PhD student, Raghu. And this software, if you have your phase profile, when you upload it, it will give you the meta-optic profile you need for there are libraries. You can pick the wavelength of choice, and then you can also say how many phase levels you want, and it will give you the meta-optic code for that. In this case, it generates what is the GDS2 file, which is required, say, for the lithography tool. So you now have your phase already, and you also have it in a format that is useful for the fabrication. So of course, a large part of this work concentrates on the fabrication because there are a lot of challenges there. So we have optimized a fabrication process that works well for meta-atoms. Remember, the meta-atoms, right now I'm only talking about cylindrical meta-atoms. These are polarization independent. You were going to vary the size, the diameter of these atoms to get the different phase levels. And of course, since it's meta, these sizes all have to be sub-wavelength, and that's where the challenge is in making let's say 8 different levels of sub-wavelength structures. So this process involves coating of a dielectric material. This material is actually the one that's going to have the meta-atoms. But in order to transfer the pattern into that, we will use an e-beam lithography writing system, and we are going to have to use a lift-off method and etching to transfer the pattern onto the dielectric. Our choice of dielectric material is very important. If you're working in the infrared, you can easily use silicon or some form polysilicon. Even though we're working in 600 nanometers and above, we have been using silicon. But if you want to go any lower in the visible region, you would have to use a different material. And it's important to use a material for which some standard deposition is available. Now, we have designed or arrived at a model for the sizes of these cylinders based on the material properties. So the nice thing about doing your deposition is you can actually go back and measure the material, the optical constants of the material, the refractive index and so on. And you can go back to your model, input those numbers if they are different from what you had, so that your design actually takes into account exactly the material properties that you have. And so this is really very important because it eliminates any errors that would come from this step of the fabrication process. The next critical stage, of course, is the e-beam lithography. So we want to do sub-wavelength structures. You have different means of transferring. You could use a positive photoresist, which is what we do. But then this means you need to have a lift-off and subsequent etching. You could also use the negative resistors mask, but this is not what we have done. And the electron beam lithography parameters all have to be very carefully optimized. Now, the problem is if you want high resolution because we have small feature sizes, but you can see that you need much longer doses if you're doing this high current voltages here, accelerating voltages. And so you have a lot of different trade-offs with the different electron beam settings. Maybe I skip this and just go straight to the challenges. So we need to have a thick resist layer because this enables the lift-off process to take place easier. And we also want a high accelerating voltage because that gives us better resolution, but it also increases the writing time. So you could increase the aperture setting of your e-beam system to reduce the time, but then this will decrease the depth of focus, which means that the thicker resist won't get fully exposed. So we have to play around with these different parameters, and we have done that and arrived at a set of parameters that works for our e-beam system, given that the maximum accelerating voltage we could go to was 30 kilovolts. Also different techniques you can do for the metal coating, and we found thermal evaporation gave us a good layer, and so that is what we were sticking to for the metal that will be used as the mask for the subsequent etching. You can see in the lift-off process, in order to finally get rid of the resist, you might have to do some ultrasonication, but you have to be, again, very careful on the length of time that you're doing it for, because a very small feature sizes may be destroyed in that process. So again, a lot of optimization there. And you can see that if the liftoff is not proper, you have areas where the liftoff has not happened at all, as seen over here. And before optimization, we had whole swabs of the element which were removed, and after optimization, you could see that we had this whole structure developed properly. Okay, so this is just an example of an Axicon and the Bessel beam output. The holographic work is work in progress, and I'm not going to be giving you the details of those results now. But let me wind up by saying that with holography, we're able to create the kind of patterns that we need in a much more efficient way than using an annular method, in this case, or an amplitude method. And meta-optics is definitely a way of manipulating light. And achieving this, of course, there are quite a few design and fabrication challenges, but with careful optimization, they can be overcome. The work I presented rests heavily on former students as well as current students. And this is my group. And here's Vijay from when he did his PhD quite some time back with me. And I must, of course, acknowledge all my funding agencies, as well as my various collaborators who have helped in my work at various points of time. So with that, I thank all of you. Thank you.